boxes. So you want to create 64 boxes, each with maybe 10 points. And then you want to calculate this thing, and then also calculate this thing. And the question is how to determine this box here, and how to determine these boxes here. So usually what we do in FMM is we have a numbering scheme. Yeah, why don't we do this? We can number these boxes with 3 numbers. So in the x direction, we have this one is 0. And in the y direction, this one is also 0. And so we number them 0, 1, 2, 3, 0, 1, 2, 3 in each direction. And we can have 3 numbers being assigned to each box. That way, we can just loop over each of the box numbers to find a particular box. That would be, I think, the easiest way to find which boxes belong to this group and which boxes belong to this group. So, yeah, maybe. Yeah, let's do this incrementally. So first, I think we should do the box finding program without the calculation, because this, if you add all the calculation, it becomes complicated. So what we want to do is to do like a box finding algorithm that finds this one, the near field, and the one that finds the far. So like a box finding program. So let's try to write a box finding program. Okay, so let's open a new code. So let's say maybe we should copy step1.c to step 2. So now we have step 2. Okay. So now I'm opening step 2. So this function is step 2. And I will leave the previous code. I'm going to continue after the previous code, because I'll be using this previous part anyway. So now, how do we do the box finding? So let's say we define the box number. Let's say I know what. Let's not create any boxes. Maybe it's easier if I. So here's what we'll do. We just create the same. We use the same distribution we are using now. We just create many copies of them. This is much easier. So what we do is say that this is from 0 to 1 and 0 to 1. We just move this one in this direction 1, and then the coordinates are just shifted from here to here. And we just use that and consider that to be this box here. We don't actually create many boxes. We're going to artificially create a copy of one box and just move it around to all these different locations. And that way, we can actually sort of emulate the behavior of all these boxes. So I'm going to create just one box, or maybe 2 boxes that we had originally. And what I'm going to do is just move this one so that it's here, 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 and just calculate the interaction as if it were calculating all these different ones. So yeah, that way we can reuse most of the code we wrote here, because I'm just going to use this one, and then this one I'm just going to move to different places to calculate this, and then the step we used here, I'm just going to move to different places to calculate this one. So let's see if that works, and because it's an easier code to write. So let's say xi, I'm going to calculate the same step as step 2. So where's step 2? This one. So step 2, I have xip, xjp. These numbers I can just change. So how do I do this? It's x. So xip is what now? Okay, 0.5 plus distance. So I don't need this distance thing anymore. I'm just going to reuse this code. Okay. So the part that changes is step 2, and also step 3. Step 1 is the same, because we assume that all these boxes contain the same information. We just move them to the different positions. So step 1, we calculate for just one box, and then we assume that these are all the same. They contain all the same Q. So the Q is the same for all of these boxes. Now, when we calculate this one, we need to make sure that we move the red boxes to each position in this picture. So first, the blue box is here, and then we need to calculate for the red boxes that are far away, like in all these locations. And then the blue box moves here, here, gradually moves around, and the red boxes we need to find accordingly. So each of these boxes here, we need to assign. So let's okay, so it's the xi and yi, zi that change. So now it's all 0.5. They're both 0.5, 0.5, 0.5. But okay, I think this is done best inside a loop. So we go from, let's say, there's 4. Okay, but we need to move it in each direction, so it needs to move in like the x, y, and z direction. So x, in the x direction it goes from 0 to 3, and in each direction it moves. So it moves like this. It moves like z, z, z. Okay, so this is the blue. When you do this, what you're doing is this loop x going from 0 to 4 is the blue box is moving from, like here to here. In the y direction, it's moving in this direction, and this z is moving in the other direction. And now, what we have to do is we need to figure out how to move the red one. So there's going to be another 3 loops for the jx, jy, jz. And what we're going to do is we do like a if statement saying if ix and iy, or ix and jx are close or next to each other, then we do this one. If it's not, then we do the other one. So we just need to loop 3 times more for the j. So I'm just going to copy. So it's many loops, but each loop is only 4 times, so it's not very much work. I just need to make sure to change jx, jx, jy, jy, jy. Okay, so now we created 6 loops to find each of the boxes. And now, so we need to make sure the distance between ix and jx, so I think we need to take the absolute value. If this is, so 1 is okay. If it's like a distance of 1, that means it's, no, I mean, we need to have this condition and iy minus jy less than 2, and iz, jz less than 2. So this is the condition which says this. If it's this condition, that means it's near. Otherwise, it's far. Yeah, so this will give you the 2 necessary cases. I think you'll see on the screen. So this near and far that I showed in the slides. So if ix minus jx, and you're looping from 0 to 4, if these 2 numbers are either 0 or 1, this means it will be 0 or 1. If it's 2, it won't satisfy this condition. So if it's 0 or 1, it's inside this domain here, somewhere. And these are connected with the AND, because if either of them are 2 or larger, then they might be neighboring in this direction, but they'll be far in the other direction, so it's okay. They just need to be far in some direction. So unless they're this and this and this, they're not close. So if they satisfy this, that means they're close. We will calculate this near equation But with the shift, so this is the amount of shifting that we can that we need to do. So we just need to add ix to the x and iy to the y, iz to the z, or jx to the x and jy to the y and jz to the z, j. So just do the calculation, the same calculation, but with the distance. So the distance is relative. So what we need to think about is just the difference between okay, so when we're calculating the near equation, we actually need to loop over all the points. So we need to loop over, oh, I need to add, I forgot to declare the j. So let's loop over all the bodies inside I, the target box, the blue box. And then we also loop over all the bodies inside the J box. So now the code is getting quite wide, so maybe it's a little bit difficult to see. But okay. Maybe I can reduce the size of the font so you can see a larger screen. Okay. So now we're looping inside both boxes, all the particles inside each box. But now, when we calculate the distance, we do something special. So this is the standard positioning, but we assume that xi is like shifted by ix and xj is shifted by jx. So this is the actual distance that we're calculating. So same for y and z. So dy dz, we assume that they are shifted according to these values here. So the numbers that are ix, iy, iz, jx, jy, jz, these numbers are the amount. So this number tells you which box you're actually looking at. So if jx is 1, then xj is that much moved. And same for I. If ix is 3, for example, then xi should be moved 3. And because the distribution of these inside these boxes goes from 0 to 1, and these are in increments of 1, it goes from 0 to 1, and then 1 to 2, 2 to 3, 3 to 4, like we want it to. So, and same for this side. So we're just artificially creating this 4x4 size box and calculating the points inside them by assuming that each box contains like a similar distribution of x, y, and z. So it's sort of a fake problem, but we'll assume that they have the same distribution inside each box. Okay, so now we have the distance. We can calculate r from, where's the r? I'll just copy this one. I'll just copy over this calculation of r from these dx, dy, and dz. And from this r, I can calculate the ui, I, and make sure to add to the previous value because this is just adding And Qj, you don't need to add anything. This is just the charge. It's not moved, or you don't need to add any value, special value here. Okay, so I mentioned that in the previous example, all the points were far, so the r would never be 0. But in this case, since when for example, ix and jx, iy and jy, iz and jz are all equal, then there's one case when I equals j that this r will be 0. So we need to avoid this case, because otherwise we'll have a number infinity. So to avoid this, we can say if I equals j and no, even easier if we simply if r is 0, r is not 0, we do this calculation here. Okay? If r is 0, we don't do this calculation. Just to avoid dividing by 0. Okay, now we move to the... Oh, maybe I'll close this other window because it's easier to see. Okay. So now the other case, we need to calculate ui p, ui prime let's do so okay, this may be a problem. We can't say that ui is the same everywhere because ui needs to be different boxes. So let's see. So ui, when ui is different, we can't add to the same ui. Right now we're adding to the same ui even for the different box. So we need to either create a different ui for each box, which means we need to multiply this by 64. So we need many ui's. The other values we don't need many, but just for ui we need many. Okay, now we need to add some number that represents which box we're looking at. So let's say I box is some function of ix and then iy times 4 and iz times 16. This should give a unique index for each box because, you know, xy and then iy times 4 and iz times 16 is just one number that we can... Okay, so this will give you... And actually I can define this up here because it doesn't depend on other values. Okay, so this is the UI that we will use. And we can calculate the same way UIP. So every time we calculate UIP, we will overwrite the previous one because we don't need to save the other ones. So for UIP, we need to initialize, we need to initialize this before we loop over the J boxes. Okay. UIP, and then we need to add this to all the boxes. So now, since we don't have unique particles to deal with, we don't need this xi thing. We can just subtract the center coordinates from each other. So for the approximation part, we're just dealing with the center of the boxes, these things here. So it's actually ix minus jx and iy, jy, and iz minus jz. And that will be the distance between the center of the box. And then for r, we calculate the distance, and then QJP we can reuse. So QJP is the same for all boxes. It's 10. And then we calculate the UIP from all the J boxes, all the red boxes. So that's why it's being accumulated here. It's because there are many red boxes for each blue UIP that we are calculating. And then once at the end of this triple loop over all the J boxes, we will have one UIP that needs to be added to the UIs that we calculated earlier. So we have a loop for, over all the UIs, and we say UI, we add the UIP to the UIs. So we say UI add UIP. So this is actually step 3 done for each box. Step 3 is being done. Oh, sorry, I need to add iBox. So iBox was the index that we determined here. It's a unique index for each box. It's being used here in the direct part, and it's also being used here in the far field part. This is step 3. So, and this one is step 2. Okay, so I think now this should give us the whole solution. So that wasn't too much modification. I just took the original code and added all the loops for going through all the boxes. So step 2 became very long. But the real step 2 is actually this part here. This one is step 3. So we don't need this step 3 anymore. This is the step 3 is done inside the step 2 loop. Okay. Now to check the answer, we also need to loop over all the i's, the different I box and J boxes. So we need to have this triple loop over the, like this. And I think we also need this I box here. And we also need the J box loops, like these 3 loops here. Okay, and let's see, which order should we do? Yeah, maybe we can take the I loop in front of the J, all the J loops. So these, okay, like this. So now we have the loop over Ix, Iy, Iz, and then loop over I, Jx, Jy, Jz, and then the loop over J. And UID is a direct solution that is calculated. So now we need to change this part again to add the Ix, Iy, Iz, and the minus Jx, Jy, Jz. And then this should give you the correct answer at all the points. And this should be compared with, so if I print this, it's going to print many numbers. Now we have 64 times more numbers to print. So maybe I should restrict the number of prints, but this I plus I box compared with UID should be the comparison. Okay, so now I will use my screen to execute on the okay. So I'll run this now. Step 2. Okay, it's printing many numbers and they seem to be okay, there's one number that's very different. Okay, yeah, there's something not working with this one. Maybe I forgot to initialize. Yes?
I think there are some index, part index, and they should multiply by them.
Oh yeah, you're right. This one. Wait. I need to have the whole thing multiplied by. Okay, now let's see if this is step 2. Oh, good. Now now they're matching much better. I don't know if this is the limit of the accuracy. Yeah, this looks about right. Okay, so what just to summarize what I did, and I'll make sure to show you the code while I'm explaining that. Oh, no. So you can see here in step 2 what I'm doing. Maybe if I make the code even smaller. Can people still see this? Yes? Because I want to show as much of the code as possible. Okay. So just to explain what's happening. So what I'm doing is all these loops here are looping over each direction one at a time. So it's looping over all 64, 4 times 4 times 4, all 64 boxes. And this 3 loops for the I is moving the blue one. This 3 loops for the J is moving the red ones. So instead of finding blue and trying to search for the red that corresponds to this, I'm looping over everything against everything, and then using this if to determine which one it is. So I'm not doing the near one and then the far one. I'm doing them both at the same time by looping over everything against everything. And then this determines if it's near. Because if Ix and Jx are smaller than 2, that means they're either 0 or 1. That means they're either here, here, or here. And in the y direction, they're either here, here, or here. So if it satisfies this condition, that means it's close. So how I do the near calculation, I do the near calculation by looping over all the points inside the blue box I, this part here. And then looping over all the j, one box at a time. So it's only n, but they loop over all the boxes eventually by looping through all the boxes. And then I need to move the points because this xi, yi, zi, xj, yj, zj, I specified in the beginning to be between 0 and 1. So all of these numbers are still between 0 and 1. And so they would be in like the corner of this upper box here. Or no, the lower box here maybe. If you define this to be the origin, then you need to shift them according to the movement. So there's a minus sign here, so I have to put a minus sign here too. So Ix shifts the I boxes and the I particles, and Jx shifts the J particles. So it takes all the points here and moves all the points. And so when you take the distance with this value, you actually get the distance between, for example, this one and this one, this one and this one, between the boxes. And then you just calculate the distance and take, since Q is assumed to be the same for all the boxes and they're always 1, so you can calculate with this. But the problem was this UI. So I was originally thinking you could just accumulate everything into UI, but it turns out because UI means different things, UI for this box should be different from the UI from this box, and it should be different from here. So I had to make sure that this doesn't overwrite every time to a different box. So this I box, I made it so it returns like a unique index for each box. So xi, yi, iz, one combination returns a different number from others. And because I didn't have this n, it was originally incorrect. But because I'm adding it to the UI, each box number should be multiplied by the number of points in each box. And then this is like an offset for each of the boxes. And I'm looping over I, but it means different boxes every time the I box changes. And then if it's far, all I need to do is, there's no xi and xj here. I just need to calculate the distance between these two. And since I know how much I'm moving the box, the distance is just the relative positioning between the two. So if this is 1 and this is 2, the distance is minus 1. It should, and if this is 1 and 3, this distance should be 2. So it's the same thing. I calculate the distance, and then I accumulate that into UIP. Say, you see that I'm initializing UIP here. This means, because when it's inside these 3 loops, I'm looking at the same blue box. So initializing here means I'm refreshing the UIP for here, and then I loop over all the red boxes with these J loops, and each time I find one that's far, I accumulate. So this will allow me to accumulate for all the red boxes because I'm looping over all of them, and determining which ones are far. This will accumulate all the necessary ui prime to this point. But now I need to make sure that this goes into the proper ui's. So then the only thing I need to do left is to do this. So the UIP that I calculated here needs to go into the proper one that's offset by I box. It goes into the UI, and it's being added. So UI is already calculated here. All these are being added, and to that I add also this effect. So now you have the far effect being accumulated into UI here, and the direct effect, the near effect, being accumulated here. So by doing this, you are able to calculate all the necessary UIs for this calculation. And now, for checking the answer, it's actually doing something similar. So we loop over all the boxes against all the boxes. This time, I assume that everything is near. I just use near for everything. So there's no if statements. And I do the same calculation that I do for the near calculation earlier. And I use this, so why is this r not 0? Because I'm using different random numbers for xi and xj. They never become the same, actually. So yeah, I didn't have to do the r equals 0 thing, because you remember in the beginning, the very beginning, I used a different drand. So here, if I used xj equals xi, yj equals yi, zj equals zi, then I would have to worry about r becoming 0. But since these are generated from different random numbers, it actually looks like for the I blue boxes, the particle distributions are different. So it's actually not doing the the same interaction as I showed here. It's doing something slightly different, but it gives you the idea of being able to calculate the near far decomposition. It's still, the concept still works in this code. So I think we covered what I wanted to do for today. It's basically, I wanted to have something that can calculate the near and far decomposition. To do this properly, you need to know the things I will describe tomorrow, which is like the how to construct the tree and how to bin the particles into each of the boxes. These sort of data manipulation techniques I will describe tomorrow in the lecture. So once you can do that, I'll write a much cleaner code for this one. But for today, you just need to do some artificial or fake way of doing this interaction between the boxes for the near and far field separately. So conceptually, we see that it's working. That if you look at the numbers that was returned, it's where did it go? So I'll just run again. Yeah, so you see the numbers are quite similar. They're like 200 something. If you go up, yeah, they're all very similar numbers. Yeah, okay, so you have these. But with the current first order approximation, this is the limit of the accuracy that you'll probably get. So the first number might be matching, but the second number will not be matching. So when you introduce the multiple expansions that I described later in today's lecture, you can increase the accuracy of this one. But for now, I think this is a good first day. If we can do this much in the first day, then we have 4 more days. So I think you can do a very fast you know, calculation in the last hands-on. You'll have a very fast code by then. So today you don't have to worry. Just you know, I'll make all the slides and the codes available anyway, so you can review them and make sure that you sort of understand the concept. But from tomorrow we will work more on the data structures so that you can easily calculate things like this. So how to find, just to give you a heads up on what you'll be seeing tomorrow. So tomorrow is the tree structure, and so there's a specific numbering scheme that sort of uses a space-filling curve, either the z-curve called the Morton index, or the one that looks like this is called the Hilbert index. This allows you to number the whole space, even if it's in 2D or 3D. It just gives you, if you know this number, then you know where it is in the space. So from this number, you can grab the information you need. So this was this thing that was missing today. But once you have this technique, you can grab any box anywhere just from this one number. It's like a address in the three-dimensional space. So from tomorrow, we will discuss a bit of this data structure. Once you master this data structure, it's very easy for you to find what's close, what's your neighbor, what's far, what's your parent, what's your child. And so this freedom gives you a lot of, you can do this in different ways, but I'll explain tomorrow. You can use like structures that have parent and child and multiple inside them, or you can use like a one index to determine the parent. You don't need a pointer. You can actually do this through division and multiplication to find the index, and then you can grab it explicitly. So many ways to do this, and I'll describe this tomorrow. But for today, I think we are finished with the hands-on. So thank you. Oh, yeah. Questions? Yeah. If you have any questions, well, we can continue if you want. How long is this room open?
I think you'll keep.
You can. Okay. So
if
yes.
you want, you can stay here. Yeah.
So yeah, I can continue looking at, you know, if you weren't able to follow the code, you can stay a bit longer, and I can take a look at your code and see how to, you know, help you make it work before you go. So yeah. Okay. So but if you're all finished and if you're satisfied, then you can go to lunch. So you said we have a lunch here?
So we'll have a lunch box here. So
Okay. We have.
can,
Okay. So you can, so that means everyone can stay.